go. We laugh. Right. So with hashing, please note that yesterday I explained the classical implementation of a hash table with linear probing. In the textbook, they have a slightly different implementation. Jessie, vergeet ek om die video af te sit, wag. Duh. They have a slightly different implementation in the textbook. You may follow the textbook's explanation or mine. So in the textbook, they have two separate arrays. The one stores the keys and the other one stores the values, and then they map the two indices to match them. You don't need to do that, and I explained it without it. But it has no influence on the implementation other than that you use slightly more memory. Okay, so logically, conceptually, it's the same. Okay. Right, so let's recap where we are. The idea is, if I give you any kind of key, whether a string, a date, a float, an integer, whatever, I can apply a good hashing function to it. And it's essential for hashing to work that it's a good hashing function. Yes. And what I get if I hash my key is a small integer value. And I suggested that you go find out what does small mean on an Arga computer, right? Okay. It is absolutely critical to the mathematical analysis of hashing that we have the hash keys, in other words, the answers I get back. I'm not sure where I am. I'm just yabbering. There I am, page 462. It is absolutely essential for hashing to work that you have, that the hashing function gives me an even distribution of keys. Yes, so I have a few keys and then a gap and a few keys and a gap and a few keys and a gap, evenly distributed. Why is that essential? Well, if that doesn't work and I get a large cluster of keys all bundled together, then the collision resolution will be very expensive. Okay? The other thing about the hashing function, efficient to compute, so you cannot have this very intricate thing, and essential that if I give you the same key, I must get the same hash value. Hash value back. At least it's amusing if I can't speak English. Okay. However, on two different keys, I might get the same value back. Yes, because there's no function that will guarantee uniqueness. Well, there are, but it's not useful for hashing. In that case, I have a collision. So what do we do with collisions? Well, the first one we briefly talked about yesterday was, if I have the array, not like this, but anyway. If I have the array and I somehow find my key and I have my value, and I find a value and it's the wrong one, I simply, with linear probing, look at the next value. And if it's not that one, I look at the next value again. So linearly, you walk ahead, okay? Which means that the bigger my cluster of values that are filled in the hash table, the longer it will get me to get to the right one. Yes. So for linear probing to, well, linear probing will always work, of course, but to have a good time complexity, I have to make sure that my cluster length is small. Okay. So that's the one thing, linear probing. The other option is, if I hash and I get a collision, I keep a linked list next to my collision, next to my, I keep a linked list next to my value, yes, and all my collisions are put into the linked list. And it's really comme ci, comme ça, which of these two methods you use, and it pretty much works out the same. The idea for the mathematical analysis is, again, it's a short linked list. Yes. If I hit too many collisions and my linked list becomes very long, then I have linear time complexity walking through the linked list to find the correct one, and it doesn't work. Okay. So what we are going to look at today, so there's your picture. They call it, yeah, meneer Sleepers.
Is it not to say we have to work out the function, is bottom stage a negative function?
Aha, I'm going to refer you back to the textbook on that one. Sorry. That's what I said yesterday. You should read those 2 or 3 pages on how exactly to do the Java so that my hashing function will work on any data type. Yeah.
Is it possible to add balance searching to
Well, you could add a link to the root. The question, did you hear the question? Is it possible to add a balanced search tree, well, inside here or hanging on? You could. What would be the advantages and disadvantages? But in real terms, yes, it will be very fast. Comment, Mr. Lang.
Unnecessary because the link list is supposed to be quite small, so that I think the search tree would be too much for the
Mr. Lang says it's simply overkill. You can, but it's overkill, and I tend to agree with him. Yes, you could, but the thing is, we specify explicitly that the hashing function must be of such a nature that you will always have a small cluster length. And if we're talking small, we're talking 5 or 10 items. Yeah, not as in some function of n, it's really, really small. Okay? And it is possible to find such hashing functions. Remember I said your homework is to go read up on hashing functions and how they work? Yep, yep, hint, hint, nudge, nudge, wink, wink in the test. Maybe, maybe not. But it's interesting anyway from a mathematical point of view. So if I have a good hash function, it would not be necessary to go the balanced search tree route. But you could. There's nothing that stops you from doing that as far as the coding is concerned. But in general, okay, so if I need a balanced search tree because my clusters are becoming too big, that means that my hashing function is not good enough. So I rather use a different hashing function. Okay. Right, so the two ways of handling collisions, either keep a linked list next to the item where I find the collision, or do linear probing. And as far as complexity is concerned, it's sort of the same thing. The book uses linear probing, yes, and they also explain this linked list idea, and they call it separate chaining. Okay. But what I want to do today is this. Suppose I'm doing this whole linked list idea. So I'm using separate chaining. How can we be sure that things will still be fast? And this is a very nice mathematical analysis of the behavior. So Ms. Coetzee mark proposition K as something you have to know for the test. And I like this because this is the first time we're not using the classical recurrence relation analysis. With all the previous proofs we did up to now, we set up a recurrence relation, and then you take C0 and C1 and you write down your relation and you do your substitutions and you keep on the pattern, and wabbity-wah, out jumps the answer. Okay? What's nice about this one is that we analyze this behavior, or the time, okay? We analyze the time complexity in a statistical manner, right? So with the mathematical analysis you do in computer science, you can go one of two routes. You can go your typical algebraic route in a certain sense. That's where we did the recurrence relations. Or yeah, a bit more calculus maybe. Or you can do statistics. Statistics is becoming extremely important in computer science, because with the advent of big data, or the possibility of big data, it is becoming impossible to analyze things directly. As an example, do you know how Google Translate works? Hoekom nie? Right, so here's one way of doing machine translation. I can say, oh, let's define the grammar of the source language. Say I want to translate from English to Afrikaans. Here is the grammar rules of English, and here are the grammar rules of Afrikaans. So I analyze my English sentence, yes, to get the grammar structure. Then I map it, I transform that English grammar rule structure to the Afrikaans one, and I simply replace the words. Yes, so that is rule-based machine translation. That was done the first time successfully in 1976, incidentally, where weather reports were translated in, I can't remember from what to what. By that time, it was probably Russian and English or something. I don't know. And they had a 96% correctness in their translations, which is absolutely stunning. Yeah, and everybody was jumping up and down about machine translation and how well it works, and the poor linguists thought they would have to get other jobs and so on. But the reason why it worked is it was a rule-based system, and the context was absolutely unambiguous. If I'm talking about the weather, a thunderstorm is a donderstorm, and there's no way that I can translate thunderstorm into something else. Yes, very, very restrictive domain with no ambiguity. However, if you take natural language, how about idioms? How about the semantic context? If I'm talking to you, my language style is much different from when I talk to my children, right? I often, because I did not speak English as a teenager, I often say very funny things and the class lie on the floor laughing in English because I never went through that teenage era of talking English, right? The famous one was, this algorithm turns me on. And in Afrikaans, I can say that, jessie nee, hierdie is nou mooi, het draai my aan. Meaning that it makes me excited. However, if you say it in English in front of a class, it somewhat gets a different meaning. Okay, which I did not realize. Okay, so there is a context, and anything you say has the potential of being highly ambiguous, and the rule-based translations can't catch that. Okay, therefore, 10 years ago, 15 years ago, if you Google translated, it took you about 3 tries to get absolute gibberish out. You could translate, say, English to French, that very same French answer back to English, and so on, and do that once or twice, and you get absolute gibberish out, right? That is because it's a rule-based translation with no context. How does Google work now? Google now uses statistical translation. You may have noticed the translations are somewhat better. So what they have is millions. And the key here is that you have to have lots and lots and lots and lots and lots of data, otherwise it doesn't work. They have millions of sentences in a pair of languages, which were translated by hand. Yeah. So there would be, die appel val nie ver van die boom af nie. The apple, what's the English for that? Oh, it's the same. Ah, yes, okay, swak voorbeeld. Die kat aan die stert beet. That's not an English one, right? Ek het die kat aan die stert beet. I'm holding on to the cat's tail, yes. Actually, it's an Afrikaans idiom that means you understand incorrectly, yes. So, however, stop that child, he's got the cat by the tail, actually means there's this little 2-year-old monster and he's killing my cat, right? Please stop him, right? So there are different situations, different contexts where the same thing can have different meanings. Okay, the one is literal, the one is an idiom. It's idiomatic. So what Google does now is they have millions of translated sentences. And then when you ask them to translate a sentence, they find that sentence in all their translations, say there are 35 of them. And then they look at the translations, and not all the translations are the same, right? And they count which one occurs most often, and they use that as the translation. So there's no magic to it anymore. You simply count. Statistics is about counting. Okay? But that's the way the world is going. And computer science as well. If you can't do stats, you can't do machine learning. You can't, yeah.
So if you translate to, say, Spanish, Surely the more often you send,
I'm not sure exactly, that is the concept. I'm not sure exactly how Google fine-tunes. They might have different data sets for different locations. That is a possibility. I don't know how they work on the inside, but the concept stays the same. So the question here was, my data sets would tend to be different depending on where I am. So if I translate from English to Spanish or the other way around, while I'm in America or while I am in China, I might have different occurrences of the number of times that certain translations occur. That means you tune your data set and you check your algorithm on which data set to use. Okay? But the principle is simply that I count what occurs more often and I say that is the answer. Okay? Which is a very, very crude way to do it, but lo and behold, it works quite well. And the interesting thing is that this works far better than rule-based translation. Because the rule-based translation is simply too complex. Remember that computers are good with syntax, they're not good with ambiguity. So the moment you have a problem that is inherently ambiguous, no matter how intricate your algorithms are, you will not be able to catch the ambiguity or resolve the ambiguity. Okay? Right, so statistics. And therefore, this is why I really, really like proposition K, because for the first time now in this course, we are going to look at things statistically. Okay, so in a separate chaining hash table, the one with the linked lists for collisions, and the size of the table is n, so I can store n keys. Yes. And I have m lists. Yeah, so there are m times that a collision can occur in this table. The probability that the number of keys in a list is within a small constant factor of n divided by m is very near to 1. You have it? I have n keys, I have m lists. The probability that the lists are short is very high. Yes? And what is the factor? Well, I have n keys and I have m lists, so my factor is n divided by m. That is the quantity that I'm looking at. Yes? So n divided by m is my measurement. Okay? What is this asking? This is asking how many times will I hit a collision in this damn hash table? Yes? M times, because that's a number of lists. So if my size of my hash table is n, how many times will I hit a collision? That is n upon m. Yes? So let's look at the maths. Remember, assumption J is that one about the even distribution, right? So we are going to look at the following. I am going to worry about the probability that a given list will contain exactly k keys. Yes? So I worry about the length of the lists. I know how many collisions I will get. Yes, I quantify that by n divided by m. That is my collision rate if you want. But now I want to know what is the size of those linked lists. Let's call it k. And I'm not going to analyze it analytically. I'm going to say, let's look at the probability that the size is k. Yeah? And look at this nice probability that we get here. Ai, Here, nou verlaat my Engels my weer. Statistically. Okay, is that what you called it last year? Right. N choose K. So how many times can I choose K from N? Combinaties. Yeah. How many times can I choose N from K? And then, why do I want to choose K out of my N keys? Because those keys hash to that given list. So I'm looking at one specific list. I'm asking, what is the probability that it has size K? Well, it has size K if I hash to that value K times. Yeah? So N choose K. Well, those K keys hash to that list with what probability? Probability 1 upon M. Yes, because there are M collisions in the whole thing, and I'm looking at one of them. Yes, 1 upon M. And then I combine the fact that the other N minus K keys do not hash with probability 1 minus 1 upon M. Okay, and there we have a lovely binomial distribution, which you did last year. Yes, okay, binomial verdeling. To make this read easier, we write N upon M as alpha, and then we get the expression N choose K, in combination K, alpha upon N to the K, 1 minus alpha on N to the N minus K. Okay. Again, what does that represent? That is the probability that a given list, one of them, has size K. And lo and behold, if I make alpha small enough, what is alpha? N upon N. If I make that small enough, that is a Poisson distribution. In Afrikaans 'n mooi Poisson. Dit is baie makliker om te sê. Okay, Poisson distribution, which we know all the properties about. Yes, so now I get known distributions. I have probabilities, I get the known distributions, and it's very easy to calculate an average. Okay, there we go. So the probability, what was T? Sorry, they rewrote that. Where's T? Oh, T alpha keys is bounded. So then I can find the bound, yes, in terms of the Poisson distribution. And this probability is extremely small. So all we are saying is that if I do separate chaining, the probability is very small that the list will become long. Right? It's very easy to calculate an average because you have it as a parameter of the distribution. Ja, meneer Sleer.
How do the graphs actually work? What we don't have information.
Okay. So how do the graphs work? Well, what you can do is what they actually did in the, which is not part of the proof. Your proof ends here, right? And then they discuss, for example, suppose I know I have an average list length. Yes, this thing. of a physical constant number 10, yes, which is small. And I have a key value. I want to look at the probability that we hash to some list with more than 20 keys on it, and then I can say what that probability is. So what you do is, I didn't even look at the graphs. It didn't make sense. I'm not a visual person. I just look at the expression and substituting values into it. Okay. So basically, you have a function, you have parameters that you put into it, and now we translate to find what is the probability that I will hit a large cluster. So I give values to n, I give values to m. Alpha is absolutely important over here, okay? And alpha is n upon m. So you simply, I ignored the graph. I'm not a visual person. I don't understand those graphs initially. I have no idea what those graphs mean. I know what the numbers mean. Yes? Anyway, I can probably sit down and figure it out. Let's see what they said. Oh, it calculates, it simply graphs the probability of, yeah. Okay. So substitute values for n, substitute values for m, and then you get the probability that you will hit a large cluster. What is a large cluster? You can ask yourself with this formula simply, what is the probability, if these are my parameters, what is the probability that I will hit a long cluster? So there was actually almost no calculation. Yeah, you simply substituted the value, used the statistical selection, the known distributions that we know from stats, and wobbly, out comes your answer. I think it's beautiful. Okay. Blah, 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 property L, you can have a look at it. We're not going to do the stats, it's a bit hairy. How many of you are doing math stats? Please do continue with it. It's very useful. I cannot do statistics at all. I don't understand it. I barely passed math stats in my second year. It's one of those things. It doesn't make sense to me. But the first time I heard about a probability was when I hit my first year. The maths school curriculum has changed. So you start in primary school with probabilities and stats already. And so I think you get a better idea of what it means. You get a gut feeling. Anyway, I never got gut feeling for stats. You do know that in your honors year, we have a special stream where you can actually do a focused data science. So you can do either a BSc computer science honors straight, or BSc computer science honors focused data science. That means you do half of your subjects at math stats and, well, 3, and the other 3 and your project in computer science, or you can follow the same route in the BCom faculty. If you do math stats, you can also specialize somewhat more to computer science. So you do your straight math stats with selected subjects, like machine learning and that kind of thing, but you have a larger, you have the choice of doing 3 computer science subjects as well. Okay. And apparently companies tell me they want data analysts now, and seriously, and please, urgently. So if you do that and you manage that, you'll get a large, potentially, now is the time, until the fad changes. But now is the time to write your salary check if you can do that. But it's a tough course. I mean, I think math stats is difficult enough as it is. But if you can combine, you're good to go. Okay, so we have that, hashing with linear probing. The same idea, so you can read through this. Here I found the table on page 472, somewhat illuminating. This looks at clusters. So this is a representation of a hash table. Of course, a hash table is linear, but this is being presented 2D just to put it into a more visual representation. And every little black dot means this space is filled in the hash table. Okay. If you use linear probing, this table represents the fact that you can potentially get long clusters. Oh, I promised no long clusters. We just proved in proposition K that we won't get long clusters. So what the hell is cooking here? What is cooking is the value of alpha. All right, man, dis my Engels. Yes. Okay. Wat's aan die gang? How do I say that in English? What's happening? It's the value of alpha, right? Because the top table is alpha with a value of a half. What is that? N upon M, right? It's alpha. If alpha has the value of half, you get long clusters. If I change alpha to 1/4, I get a much more decent distribution. You actually struggle to see clusters longer than 5 over there, right? So clearly, what is alpha? N upon M. So the ratio of the size of my table against, what is M again? No, the number of lists. So the number of collisions. So it's the size of the table N against M, which is the number of collisions I get. The smaller it becomes, the smaller my clusters become. Which means what? I waste a lot of memory. Yes? If I make M to M, yes, N upon M, the larger it becomes, the longer my clusters get. And you can see that in your statistical distributions in proposition K as well. Look at the value of alpha. Where does it go to? Why does a larger alpha imply more longer clusters? So typically what you want when you look at a hashing function is you want to make sure on the one hand that my table is large enough. Yes. You want your table to be large enough, the value of N, so that when I apply my known hashing function to it, I won't get too many collisions. So the guy at the top tried to save memory. So if I increase the value of N, yes, remember all my hashing functions are mod N. Think about this for a second. I have some or other key X and I'm hashing. Never mind what my hashing function is, somehow at the end, it must have a mod N so that I return a small integer value between 0 and n minus 1. So I have to mod n, yes. If I make n too small, yes, the smaller n, the less choices I have, yeah. Imagine mod 5. What are my choices? 0, 1, 2, 3, 4. Mod 10, I have 10 choices. Yeah. So if I increase the size of n from 5 to 10, to make it a blackboard example, yes, not a practical one, clearly there are more places where when I do my hashing, I will have less duplicate keys. I will have less collisions. As easy as that. So in practical terms, what does this mean then? This means that I must make my n big enough. So in a certain sense, I will waste memory, but I will make the thing faster. If I say memory is an issue, then don't hash. As simple as that. Okay, because if you have to restrict your memory, you will hit long clusters. Okay. Thank you very much. We are, you have to know proposition M, but not the proof. Yes? Whoops. So you have to know this answer. Incidentally, if you don't know who Donald Knuth is, go Google him. That will be a icing sugar question in the test, potentially. Who is Donald Knuth? Please know this result, and then you have to look at array resizing. Ja, ek het nou weer te veel nonsens gepraat. And I know that we never look at the last section in any chapter. So 3.5 is not for the test except for this table. This is a summary on page 487. That summary you have to know. Okay? Good. Thank you. I'll see you on Monday, and then we are going to start with chapter 4. Only 2 chapters left for the rest. Yeah, 4 and 5. Cool. Thank you very much.